I should introduce myself. I am Hannah Peterson, and before I worked with EMI, I did work in the U.S. Air Force in data acquisitions, diesel generator work at Cummins, and solar power with Fronius and Newsun. So I have 10 years of industry experience before I joined EMI, and then I've been with EMI about 5 years. And I am an associate staff. I'm with the U.S. office, but right now I'm based in Africa. So, I mean, at the moment, obviously, I'm not in Africa. I'm here on a visit to the U.S. All right, so the three basic areas I'm going to try to cover are just to introduce the energy resources and sources that we might be considering, then give you just a little background on energy storage. I didn't have time to put a lot of information on that, which is fine given the audience we have here. And then I'm going to spend some time on the cost analysis tool and how to use that. It's a really powerful spreadsheet, but it can be intimidating. So the first energy source I want to cover is the most common, the utility. The price on utility in the developing world is extremely variable. You'd think, okay, maybe it's low, maybe it's high, and it would be uniform, but it's not. We've got everything from, I went to Zambia and saw 3 cents a kilowatt hour, which is changing now. They're trying to increase their rates, all the way up to Haiti, which is 35 cents per kilowatt hour right now. And that really changes what sources you recommend. We try to recommend to our customers what financially is going to make sense for them and allow their total cost of energy to be the least expensive possible for them. And sometimes that's hard because you come into a site and it's changing. They're telling you, well, the rates are going to increase. And we usually just say, if they're telling you that, unless you have it in writing, just go with whatever their rate is now, ask for the energy bill, and actually look at the real rates. And then when the utility company actually gives you a letter and says they're going to increase, then I would consider that. But until then, there's always like rumors of it's going to increase, but I wouldn't base financial analysis on that. The voltage in our context is almost 100% Y. That won't mean anything to non-electricals, but to electricals that's important. In the US, we have a lot of variety. In the developing world, in general, it's Y, and it's 400 volt, 230 volt range. It's somewhere close to that, usually. There should be plus or minus 5% nominal at the transformer, but we have seen as much as plus or minus 10% at a utility transformer. So it is worth checking, but know that most customers will blame everything on the utility, and that may or may not be the case. That's why we take power analyzer data. The availability is one of the things that you enter into the spreadsheet. So I want to cover a little bit what that was. This is when the utility is present as a percent of like the total hours in a day. And this is something that's really variable on its country and also if they're using hydropower. And so you have to also be careful. Sometimes if you go there in dry season, they'll tell you, oh, the utility's always off. And you have to actually ask for real data. Okay, how many hours is it off? And is this all the way through the year? When was the last time you had regular power? You have to ask a lot of questions to really get down to, is this normal or is this just, I'm really hurting right now this month? And so you want to try to get the average. What is the total average? Because that really affects the financial analysis. As far as sizing transformers, I want to just cover underload and overload for the different sources because this can be something that people don't really realize. For transformers, if you underload them, it's no problem. They can just be underloaded for years and years. It just means they last longer. So there's no worry with that. If you overload them, it does shorten their lifetime, but it can handle some overload. So it'll just get hotter and last shorter time. If you're overloading extremely and they're seeing really high temperatures, it can lead to like a fire or explosion. So you want to like somewhat be worried about that, but don't worry too much about like sizing it exactly for the size. It's totally fine to do that. And in fact, that's what we want you to do. We want you to size it to the maximum average loading expected with the planned expansions for the next 5 to 10 years. And this would be advisable if you can use sizes that are readily available. Some countries, like if you ask for, I don't know, a 400 kVA transformer, it's going to take you 3 months of feet dragging to get it. Whereas if it's 100 kVA, oh, we have 10 of those in our warehouse all the time to replace. So it's good if you can pick ones that when you talk to the utility, that's important. If you're on a site, if you can talk to the utility, ask them what their common sizes are, because that way if one fails, they can easily swap one in. As far as paralleling to the utility, for non-electricals, this means when you have any two sources and you want to actually produce power from both sources to the same load, so that what's actually consuming the power, then you've got to parallel them correctly. You can't just like flip a breaker on both of them and hope everything's okay, because it'll just destroy the system. You have to make sure they're both in synchronization, because it's AC power, so the voltage is going up and down. You want to make sure they're going up and down together. You want to make sure everything is synchronized, we call it well, and then you connect them and they parallel, and you want to make sure that one of them doesn't start pushing power to the other source. You want to make sure they're pushing power to the load. So there's some complexity involved in that and controls involved in that. So you have to be careful about how you do that. With the utility, it will always be what we call the grid former. There's always a grid former, the one that's like the master you can think of in the system. And then the other sources just follow it. They synchronize to it and they connect, and then they do controls things to be able to push power in. Let's keep it simple. So in the case of the utility, it is always the former, it never follows. The other sources can be parallel without feeding power back to the grid. That's important to understand, because if you have a solar system, you can actually be paralleling with it, so that allows you to push power into the loads that are on the site without pushing power back to the utility. It just has to be set up in the controls so that it never actually pushes power. And as far as what sources do we parallel to the utility in our context, diesel generators, we never parallel to the utility. It can be done. It is done in the US at times for peak shaving, but the utility has to like emergency call you up on the phone and say, hey, we're struggling, turn on your genset and produce 100% power, and we're going to pay you this exorbitant amount because we're desperate, basically. And that never happens that we've seen in the developing world. So we're never going to parallel the diesel generator. Solar, yes, and batteries at times, yes. And that doesn't mean we're pushing power to the utility from the batteries, but it means we are paralleling with it to shave off some of that usage from the utility. If you are going to feed power back to the utility, so anytime you have a site, you have the loads, electric's flowing from the utilities to loads. If you have excess power from solar, you may want to actually push power back to the utility, which would make the meter actually run backwards in some cases. And that requires a bidirectional meter that actually can go backwards and forwards, or 2 meters to track the export and one to track the import of power. In order to do that, when you sit down and talk with the utility, there's a few terms that come into this. One is called net metering. This is actually the best financial case, and you want to ask about this. But be aware that sometimes when you go into the developing world, what they call net metering is not net metering. So ask further questions. Don't just assume. Say, well, how much am I paying for the net metering? And ask some questions like that. Net metering is, by definition, that I basically will, so throughout the day, if you got solar, it's going to be, like at night, it doesn't produce, right? And then during the day, it produces. But in the middle of the day, it might be producing more than you're using. And so at that peak, you're going to push power back to the utility. And then at night, you're going to take more power than you normally do. And so the net metering means that at the end of a period of time, they just charge you the net of that. And so that could be every month they charge you the net. It could be they just kind of keep track of that amount, and then at the end of the year, they zero it out. But that's the most economical, because what it means is they're charging you the same amount of money as they're paying you for every kilowatt hour. And that's the most ideal, because even if they increase the rates, they're always charging you the same amount. Feed-in tariff means that they charge you a different rate. So they charge you one rate for what you buy from them, and they charge you a different rate for what you give to them. And who can guess which one's the greater, right? I mean, they're going to charge you more for what they sell you than what you give them, which isn't really fair, but that's what it is. And I went to Nepal, and they said, oh yeah, we have net metering. We pay you 7 cents a kilowatt hour for the power that you give to us, and then we charge you 13 cents for what you pull from us. So that's not really net metering, but it's feed-in tariff. And so it's important that you understand those questions to ask the utility in order to enter them into the spreadsheet correctly, because that really affects the economics as well. And it's important to talk with the utility. I have gone on multiple project trips where the project leader is like hesitant to contact the utility. The ministry is, I don't know, it's a little intimidating, but really try to get a meeting with utility if you think you're going to be doing solar, because this really affects the economics of it. And try to talk to the right person. So they'll usually take you to the local person, and that's good for a relationship. But say, no, I want to talk to the headquarters person, because you're usually going to have to go to like the capital city or talk to somebody at like a headquarters, and those in-person meetings are where you're going to get the information quickly. Don't even think you're going to like call them after you leave. Most countries, you're not even going to, you'll call and you'll just be put on hold forever. So $0 or no payment or no export allowed. Those can also be other things that you run into where they don't want anything pushed into the utility. That's usually just we don't understand it and you need to talk them through it, and being in person helps them to understand this isn't a big deal. We'll push a little power, it'll help you out, and just helping them understand that can usually get beyond that. All right, so we're gonna move on to solar. And the price per kilowatt module inverters, we're finding that it's similar across the world. So I wouldn't worry about trying to necessarily find a solar shop where you're at, because it might be hard. But I think that you can use the default values we have in the worksheet. And right now the default actually is based on a project we did in Tanzania. And I included the amount for the racking to be conservative, in the sense of like it's more than what you're going to pay for the panels. Right now, we're seeing that it ends up being 2 to 6 cents per kilowatt at 10 years is common. I can't say that's absolutely everywhere. It depends on how much sunshine you have and et cetera, but that's just to give you a ballpark of what we're talking about with solar. It's really become very inexpensive, so it becomes very economical in a lot of situations. So it's definitely worth considering in your financial analysis. The voltage of an individual module is going to be in the range of maybe 30 to 38, depending on whether it's a 60 cell or a 72 cell module. The DC voltage of strings, like full, when you string them all together, is going to be in the ballpark of 600 to 1,000 volts. That's the max voltage. That's in like the worst case conditions, cold weather and full sun. The inverter AC voltage is absolutely excellent power quality in these days. We have really good inverters, so you're not going to have to worry about power quality if you have a good system. This is just to show a graph of what solar prices have done. I sometimes have people, especially older people that aren't aware of this trend, that are like, yeah, solar never makes sense, because that's what they knew from, I don't know, 20, 30 years ago or something, and it's really changed. The prices have really dropped, and so that really changes the economics of putting in solar. Availability, when the sun is present, there's solar. When the sun is not present, there's not solar. Underload, in general, there's no negative impact of underloading in the modern systems. It is financially wasteful, but for the most part, you have a controller that will curtail the solar. So don't worry too much about putting in too many modules, like trying to get it like under the amount that needs to export. It'll just curtail them, it's fine. Overload, solar inverters and battery inverters will have a maximum rating. And so that's the absolute max they can push out. So especially if you have a completely battery and solar and you've got an inverter there that's supposed to produce for the load, if you don't have enough capacity and rating in that, then it'll just stop producing. So that can be critical. And there are many options as far as the sizing. I can't even say like this is how you size solar exactly. We're going to show you the cost analysis spreadsheet that gives you several different types of systems, and I'm going to go through what the different types are, but the sizing will greatly depend on the site and the financial analysis. Paralleling, solar will always be a grid follower. Remember I said the utility is always a grid former? The solar is always going to follow if it's connected, if it's paralleling with any source. And oftentimes in our systems that we're designing, it is paralleling with the utility battery system, which is called AC coupled, or a diesel generator. It can parallel with any of those. Not that we always do, but it can. These are solar power modules. For those who are not double E's, there is a difference between solar thermal and solar power, or photovoltaic. A lot of times there's confusion about this in the developing world. You'll come in and they'll say, oh, we want solar, and they've experienced solar thermal, and that is out of our scope. We do have some worksheets for it, and I think sometimes there's no one who's covering it, so it's okay to ask your project leader for some worksheets to to kind of give some estimates on that, but that's not expected of you. The PV is all that the electricals cover. The photovoltaic, converting the sunlight to electricity. Solar thermal is just for heating water. These are the two standard sizes, a 60 cell and a 72 cell. You're going to see in the developing world all sorts of little ones, big ones, all different shapes. Stick to these two. The smaller ones are really intended for doing like small charging for like a cell phone or doing batteries or something like, small systems. When you're talking about big systems, these are the two standard sizes. And if you use the standard size, they'll be able to replace them. It'll affect the system a little bit if there's one that breaks and you replace, but it's still at least replaceable in the future. So how do we measure solar energy? What we do is there's solar irradiance, or watts per meter squared. That's the amount of light that's striking the surface. And then irradiation is the watt hours per meter squared. And this graph is basically, so watt hours per meter squared is the integral under the curve. So this is the irradiance, or amount of sun hitting the surface at any moment. And then this is throughout the day. So at this point, what time of day do you think it is? It's noon, right? It's the most sun. And then all these little squiggles here, that's just like cloud cover, things like that happening. But in general, it takes this nice shaped curve, and it usually is starting, the max power is going to be around 8 a.m. as far as, not max power, but like when you actually want to make sure you're harvesting it. Because if you can harvest all the area under the curve from about 8 a.m. to 4 p.m., you get the majority. So that's when you want to make sure you don't have any shading. Peak sun hours. You're going to see this terminology when you're working with solar. It is the insolation divided by 1,000, and it's just the benchmark or whatever of trying to do this analysis. And you'll see here is a graph. You can see throughout Africa there's areas that are especially stronger for solar than other areas, but most areas it still makes sense to put in some. This is a website that I highly recommend. Before you go to the site even, you know where you're going, go to gyasma.com, and for every international country around the world, find the closest city. It won't necessarily have a tiny remote village, but it'll give you a close, big city. And look at the insolation values. This is per month. It gives you the average kilowatt hours per meter squared per day, which is the same as what we just talked about, the sun hours, but it's per day. And then if you're designing a system that's going to be like grid connected, you just want to know the total average for the year. So you just take all those numbers and average them. If you're going to do like an off-grid battery system, you want to look at the worst case month and then use that value in your cost analysis. This is called a sun path. I'm not going to go into these in complete detail, but the primary way I use this is that it gives me the altitude angle, which is the angle from the horizon up to where the sun is hitting at any given point in the day. And between 8 and 4, remember on that last graph, if you can get all the power between 8 and 4, you've got the majority. So you want to make sure you're not getting shading during those times. So you basically take that angle, and then you look at, like, if you have multiple modules sitting like this, you're using some trig to make sure you're not shading the modules from each other during that period of time. So I'm not going to go through the trig right now, but I'm just giving you an overview so you're aware of that in your design. And that affects also, like, if you're trying to locate a system and say you're in the middle of a city and they're a single floor building and they're surrounded by 3-story buildings, solar's not going to work very well. You're not going to get very much harvest because you're going to have shading all the time. But this helps you to do that analysis, to say where is that object that I see that's going to shade, and try to figure that out. This is what the actual curve looks like for a solar module. It's important to understand, mostly for our electrical engineers, so I don't want to spend too much time on it, but basically the concept is that at any given moment of time, these are two different sun amounts and temperatures, and that affects the production of a solar module. And you also want to have a maximum power point tracker that actually keeps it at its sweet spot to produce the most it can as well. So the controls are important. That really helps you get the maximum out of a module. I think that's one important takeaway here, instead of just doing a module without a controller. And the temperature and the sun amount will affect production. So if you hook up your solar system and it's not producing 100% of what you expected, it may just be that it's cloudy or the temperatures are hot or any number of things. And I think another piece of information that I always want to make sure you understand is that site load does not equal solar array rating. So you can't just look at the back of a solar module. The solar module is going to have 250 watts. But you can't just say 250 watts times X equals my site load. It does not work that way at all. That's completely wrong. So don't think that way when you're trying to design these systems. It's a complex, they don't actually necessarily produce even what's on the back of the module, and what you're really looking for is the total average usage of the site versus the average production of the solar. And so it's not as simple as it might seem. So I just want to go through a few different types of systems so you're aware of the different types. A lot of times in Africa, when you say solar photovoltaic, they're going to think of this. And honestly, we don't do this very much at EMI because we're mostly working on bigger sites or a big building that's getting power, not like a little village hut that we're trying to charge a cell phone off of. So this is more for a cell phone application or something very simple where you don't have any controls and it's just a very simple load. We've got off-grid standalone systems. So these are where you still have the battery and the solar module and the load, but then you have an inverter to be able to take the DC power and go to AC for the AC loads, and you'll have something to actually help to control that maximum power point so that you're harvesting the maximum amount of the solar power, you're not overcharging the battery, it's helping with the charge control, and this is the inverter, and then you often have a backup genset or a generator. We have utility interactive or genset interactive. This requires a different type of inverter. So both of these inverters are taking DC and making it into AC power. But this one's really intended to parallel with other sources. So it's allowing you to take that solar and parallel it with the utility and the generator. And then we have full-on microgrids. And I just used the simplified diagram instead of drawing absolutely all the components. But you have a brain, the microgrid controller, and it just is telling what power sources to come on when to optimize the whole system. And it takes care of optimizing all of that. So it's going to make a highest priority to the solar. It's going to try to use 100% of that power. And the battery system is to try to store the extra solar during the middle of the day for usage at night. And then you've got the utility as the second priority. And then you want to just rarely use the generator. If anything, ideal system, you just want to exercise it every once in a while to keep it healthy, but you want to reduce the amount of diesel fuel because that's always the most expensive source. The global average price for diesel generators is $3.82 a gallon, which comes out to 28 cents per kilowatt hour. What we really care about in the electrical mind is what is the dollar per kilowatt hour. That's how much you're actually paying for the energy. And so our spreadsheet has all the factors in it. All you have to know is what's the price per gallon, figure that out, enter it in the spreadsheet, and then it'll tell you what the dollars per kilowatt hour is. This can be variable. I saw countries that are way lower, way higher, but this is the average, and a lot of places we go, it's in this ballpark. The voltage on a generator will suffer if it has large load steps as a percent of the full rating of the generator. If it's possible, it's good to keep the load steps below 50% of that rating. And also to make sure that you buy a G3 ISO 8528 diesel generator if possible. There are different types of gensets that are rated for different, some more for fuel efficiency and some more for their performance. And so, especially if you have a hospital, I recommend a G3. That means it's going to have the best voltage response that's available in the market. That means it has a steady state of plus or minus 1% and plus or minus 5% or 15% during a large load step. The availability of a generator is 100% as long as there's diesel fuel. So often on sites that are enormous in the developing world, that especially if they have a hospital, something very critical, there is a backup genset in the system because no matter what, you want to have available power 100% of the time. You're probably going to have a generator involved. It's important to understand that if a generator is underloaded for long periods, which means under 30% of its rating, then it will cause damage to the generator, and this is called wet stacking. You don't want to way oversize your generator because you will have problems with it over time. And I'll have some more slides to show what that looks like later. Overloading, that's also a problem. So diesel generators are a bit touchy when you're talking about sizing, because if you overload it, if you're using the prime rating, there's actually a buffer of 10%, which helps. But if you exceed that rating, the generator will trip off or stop running. It's not like a utility transformer where it just gets a little hotter. It's like it just stops. Note that generators may not be able to accept the full 100% in a single step from startup. In cases where it is it's run near its rating, apply in 2 steps. So I've seen sites, especially one in Cameroon at a hospital there, where when they tried to put the full load on it, when they transferred over, it would just die. And it's because they were right at that limit, and especially as it gets older too, when you transfer it over, half the time it would just die. The way to solve that is just apply in 2 steps. The generator can then take the full load. This is what wet stacking looks like if it's let run. You get oozing black coming out of everywhere on the generator. If it's caught before that stage, it can be reversible. Basically what it is unburned fuel that comes out of the combustion chamber, and it results in fouled injectors, buildup, loss of engine performance, premature engine wear, and degraded oil seal. So it really causes a lot of damage to the generator, so you don't want to go that direction if you can help it. Sizing a generator, the kVA rating, this is important in order to avoid the wet stacking, should never be larger than, I would say, the current average load divided by 30%. So you're basically saying that current average load has to be able to keep the generator at 30%. And then if the above rule allows, then size the generator so that it's able to handle the maximum expected load after growth, or basically the calculated max average times 125%. So basically you're just saying the average that you're expecting, the maximum average you're expecting, and then add a little cushion in there. But you have to keep it under this number here, the current average divided by 0.3, because you don't want to wet stack a brand new gen set. Use the prime rating if they're operating it for over 500 hours a year, and use the standby rating if you're operating at less than 500 hours a year. And there's also a rating called emergency standby that's only if it's less than 200 hours a year. Most people aren't even aware there are 2 ratings, that there's a standby and a prime rating. So just be aware that there is. And if you're at a site where look for their log, ask them how many hours are you really running. If they're running it over 500 hours, which I found on a lot of sites has been the case in the developing world, you probably want to use the prime rating. And that actually is helpful because it gives you a 10% buffer for those short duration loads, like an autoclave coming on for a short period, or an X-ray or something like that. We do not tend to parallel 2 generators together because of the additional complexity of the controls to do that. We try to, as much as possible, we try to shy away from any extra controls, just because if it fails, then what do they do? I can't say this is 100% of the time. It depends on the site. Some countries are more developed than other countries. Some countries have better maintenance staff than other countries. So you just kind of have to take your engineering judgment. And if you go to a site and it's there's nobody maintaining anything, and I don't think anybody here would even know how to fix 2 generators paralleling, then just avoid it. Just split the system into 2 and put two generators there. The generator can parallel to solar, but because of that wet stacking issue we just talked about, you have to be careful that there's a controller in there to limit or curtail the solar if it's producing a ton and it would cause wet stacking to the generator. And that could be the Microgrid Controller can do that. There's also something called a fuel saver controls out there that can do that. It can also parallel utility, but like I said, we don't do that at EMI. I'm not saying never. Maybe there's a customer out there who would do it, but I haven't seen it yet. To a battery system, it is the most expensive source of power, so we would only parallel it to the battery in a very rare situation, like the battery's about to die or something. In our context, diesel generators are often the only feasible and affordable option. This is referring to other types of generators. Sometimes we get questions about what about natural gas, propane, all these other solutions. don't worry too much about that unless they're telling you like, yeah, all of our neighbors have natural gas generators, then maybe you're in a country where that actually does make sense. But most of the places we go, natural gas is not a cheap source and it's not readily available. So diesel is what they use everywhere. We also sometimes get asked about wind power. Small wind pretty much never makes sense financially. Large wind is in the 3 cents to 6 cents a kilowatt hour, so it is inexpensive, and that's why you're seeing a lot of it installed in the US. But in our context, that's typically outside of our scope. We don't typically get involved in projects with enormous wind turbines, and most of our customers aren't in locations where they can even do that. So we usually don't consider it, but I'm not saying you can't if you feel like it's a compelling reason to think about it. And the reason that small wind isn't economical is you don't really get the really high winds until you get up high enough in most places to make it economical. Large hydro, again, is a great source of power, 5 cents per kilowatt hour, so it makes sense. But on our sites, we're not putting in giant Hoover dams, and there are sites where maybe they have a river that they can use, but it's got to be something really big. Bungalow has a hydro. That hospital, but I mean, you go to the river and it's a roaring river. This isn't like a creek. So if you're at a site and there's a giant river that they like own and it's right there, maybe it makes sense to think about it, but the majority of the time we don't even think about a hydro as an option at all. So energy storage, I'm not going to go into a lot of detail, but it has to be a deep cycle battery. You don't just buy car batteries. This is a special type of battery that has to be able to take these slow but deep charge cycles. And those typically are lithium-ion AGMs, absorbent glass mat, which is a type of valve-regulated lead acid, and then fluid-filled lead acid. I do not recommend doing the fluid-filled acid in general just because of the maintenance issues in Africa and a lot of the other contexts you'll be working in. We find that people don't often want to make that commitment of watering their batteries and checking electrolyte balances and things like that. So we typically go with the low or no maintenance. Even a lithium ion, you're going to still have to have somebody come in once a year and change cooling systems and things like that. So something to be aware of. You are adding maintenance, but these are less maintenance, your lithium ion AGMs. Our default in the spreadsheet is lithium ion, and that's what I've been using on a lot of projects for my costing just because it's the lowest cost I found right now on the market. And that's the lowest cost long term. So don't be deceived when you see a lower dollar per kilowatt hour rating on some of these other solutions. You'll say, oh, lead acid's this is $135 per kilowatt hour and AGM's $225. Well, why don't you use those? They're a lot cheaper. But you have to look at the whole lifetime. How many cycles how much total kilowatt hours of energy cycling am I going to get? It's called throughput in the industry. And so you actually have to take that kilowatt per hour rating, and then you have to look at the depth of discharge. How much can I actually discharge the battery? And the battery industry is interesting in that you'd think that if you could only discharge at 50%, that this rating would be the 50%, but it's not. They give you the full rating of the entire battery and then tell you you can't actually discharge that full amount. So you have to look at the depth of discharge, and then that depth of discharge will affect the lifetime. And oftentimes there's a whole curve for this, so it's not like it's only 50%. If you discharge it 80%, this lead acid battery is going to last, a year or something, right? It's going to die very quickly. And if they're cycling at less than that, like they're only discharging a little bit, it may last more than 3 years. So it's variable based on how much you're discharging. And then you can see that lithium ion, because it can do that lifetime of 15 years at 70% depth of discharge, the total dollar per kilowatt hour over the lifetime is actually much less than these other options. So that's why we've started that's my go-to option right now. That we're getting pricing from Tesla Power Pack that is in that price range. So the price that's in the spreadsheet is based on the Tesla Power Pack. We're open to any other options. We've asked ABB for prices. We have gotten them from them, but their systems aren't small enough to fit most of the sites we're working on. So we've just found that it's a good size for what we're doing. But certainly if you're talking about a smaller system, you may talk about Outback and some other options, but that's the default in the spreadsheet. Make sure you do get a quote if you're looking for a particular type of system. Note that the Tesla Power Pack system also includes the battery charger inverter already. So those values are 0 in the spreadsheet by default, and you need to add those if you're considering another type of system. So this is the energy source cost analysis tool. It's a really powerful spreadsheet. There are 4 tabs in it: instructions, there's an input tab, a cost projection tab, and a solar insolation curve tab. I'm not going to go through the instruction tab, but it does give you some guidance. This is the input tab, and this is where you put in all of the data that you need that is specific to that site. There's also a cost projection tab that is going to give you the actual graphs of all the different possible solar systems that we have in there by default, but you're welcome to add more rows for other systems you think of. And then this graph down here is going to tell you, I actually added another one since I pasted this in, to give you a 5 and 10 year dollar per kilowatt hour value for those systems as well. And this is the solar insolation curve tab. And this is to give you an idea of the actual insolation at that site. So that's the amount of sun striking the surface per that particular geographic location. I wanted to highlight a couple things on each of the tabs. This is the input tab. This area right in here is where you enter the load data. So you're going to do a load analysis. There's a whole different spreadsheet for doing a load analysis, and we've added some new tools for being able to do by hour load estimates even for a new site. And then you'll enter the results of that spreadsheet in here. So by hour, what is our average kilowatt hours or kilowatts we're expecting? And the sum is at the bottom. We'll also enter known details like the cost for diesel fuel in dollars per gallon, utility power, you're going to talk to the utility and look at electrical bills for that, the feed-in tariffs, the utility availability, we talked about what that means, as well as the generator lifetime, which we calculate as usually 20,000 run hours, and then just divide by the number of hours you're expecting per year to get an estimate in whole years for that. And these are where those entries are at. All of the places that you're going to want to change something are a colored cell, so like a purple, green, or I don't know what the other color is, but or blue, I think. The insolation data, like I said, will be from this gyasma.com website. And also the latitude needs to be entered as well. And that just Google, what's the latitude for the closest city, or that'll come up in Google. And you can change the battery type from a drop-down here. And you can change the depth of discharge, the lifetime, prices. There's a lot of configurability in the table. So you can make it do pretty much anything you want, but we do have defaults set in there so that if you don't really know what to put in, there's a starting point. Cells for percent solar and percent battery will be adjusted up and down to optimize. So these are once you enter all that known data, then right in here, you'll be adjusting percent solar and percent battery. It's just an iterative process. We don't have software in there, so like hit go and it tells you what system to put in. You're going to have to do that manually to tweak things and find the best solution. Also to keep in mind, there is a solar constant on the insolation tab that you'll have to adjust to make sure that this value here at the bottom equals the insolation value entered on the other sheet. So this will have to be adjusted, and it'll highlight in red if it's not correct on the other sheet to flag it. These are the systems that we have in there by default. So I just wanted to spend a little time to explain what these systems are. This is self-explanatory, generator only system. It'll give you the price for that. Utility only, it's self-explanatory. Utility blessed generator means if the utility's on, it's off the utility. When the utility's off, we're running off a generator. X% solar, no battery plus utility means we are paralleling to the utility when it's available, and we're pushing power if we have more solar production than we have load. But if the utility's off, the solar's off. X% solar with Y% battery plus utility means that we have a certain percent, X% solar, I think I may have, no, I didn't do that. X% solar means it's a percent of the total usage for that site. So in a given day, there's going to be average kilowatt hours. You may take it off utility bill, you may take it off of, in your projections. that number, we're saying in the spreadsheet, you can say, well, I want 50% of that to be covered by solar, or I want 25%, or whatever. And so that's the percent solar. And then the percent battery, for the purposes of the spreadsheet, is the percent of excess solar that we're storing in battery. So if, I think I have some other plots later that kind of show that. So like during this time here, there's this much excess solar here, so it's what percent of that do I want to store in a battery? We found we're seeing a lot more systems where that's making sense, so that's why we changed it to do it that way. And then, so that's just shifting that power to other times of day plus utility. So again, this will not have, the battery, it may have some availability of power when the utility's off, but it's not necessarily all the time. It's just enough to handle the excess. X% solar, no battery plus utility plus generator means that it's basically like the solar and utility up here, where it's just paralleling utility when it's available. But if the utility is not available, then we go over to generator. And then X% solar with 5% battery plus utility plus generator plus microgrid controller. This is an all-on microgrid system. So this means if the solar is producing, it is being used. It's either paralleling to the utility, it's storing power in the batteries, or it's paralleling to the generator. It can do all of those things. So this is the maximal way, the way to get the maximal usage out of the solar, no matter maybe what the size it is. And then this last option is 100% solar, 100% battery. That's completely off-grid. There's no backup other than just the battery and the solar. So these are the defaults we have in there, but you are welcome to add any other systems, but it's important that you understand what these mean as you're going about the analysis. And there's two key questions when you're doing the cost analysis before you start. Do they need 100% power availability, and how many years forward is the ministry looking for payback period? So the first question is like, is there a hospital? Is there something where we have to have power all the time? That's important because some of the options that we have, that's not the case. So you don't want to recommend that. And then how many years forward, depending on, so this is like the cost of each one of the solutions over time. So you can tell that like here, maybe the black makes sense, but once you get further on, the green one makes sense, right? So it's important to know at what time period are we actually making this economic analysis. For this example, I'm just going to show you a quick example. The answer is yes, we need 100% power availability, and we're going to look at a 10-year payback period. So that's the number of years at which we're trying to say what is the least dollar per kilowatt hour at this point in time. Here's an example for a system with 90% solar, 100% battery, and you can see the blue is the load for the site, and the yellow is the solar production. So you can see in the middle of the day we're producing excess solar, and that's being stored in the battery for usage at other times of the day. And this is the economics, the plot of the total cost at any given year. So the total dollars that have been spent on energy from year zero at any given point per the year. And then I also have this plot in here. I colored the red ones, the ones that are 100% energy availability, and the blue ones are not 100% energy availability. And you can see at 5 years, maybe utility plus generator could make sense. But then once you get to 10 years, in this case, we've got some 20 cents per kilowatt hour. Just picking a number, just saying 90% solar, 100% battery. Just start somewhere. It isn't necessarily important your starting point. The next question is, well, can we beat that? Can we do better than 20 cents per kilowatt hour for this particular site and for that time frame desired? And so you start adjusting the solar and the battery percents to try to get below that. And the answer in this case is yes, we can get all the way down to 17 cents per kilowatt hour in this case if we use 40% solar and 180 kilowatt hour battery, which is the minimum system size with the microgrid controller allowing paralleling with the generator. So and this what this looks like here. So like in this example, you've got, $211,000 initial investment and 17 cents per kilowatt hour for like the microgrid system with 40% solar and 100% battery. So then the next question is, well, can we beat the $211K initial investment and still achieve the 17 cents per kilowatt hour. So you're going to like look at one cell and try to optimize, and then you're going to be looking at another cell and trying to keep that cell that value, because there's often a range of different sizes for which you can get that like 17 cents per kilowatt hour. And so you don't want to put in a bigger system than you need to for that initial investment if you can still get in that same amount, like that same price of electricity with a cheaper initial investment. So in this case, it was close. It might even be a rounding area, I'm not sure, but I wouldn't go any finer than 5%. I was able to get 35% solar with the 180 kilowatt hour battery and achieve that 17 cents per kilowatt hour with 159K initial investment. Like I said, don't feel like you have to go down to the 0.05 percent. It doesn't matter at that point. Just try to get in the ballpark, plus or minus 5%. A couple warnings. The cost analysis spreadsheet will let you design systems that are not feasible in real life. And so always check for feasibility. Don't just blindly use the spreadsheet. For example, a roof size may limit the size of your solar array, so don't tell them to put in a whole baseball field football field of solar if they only have this much roof space on the top. So just think about that as you're using the spreadsheet. That's why it's important you understand the systems, what they look like, how they interact, and you understand all of that as you're using the spreadsheet. You may have noticed that I said the minimum size for the battery system. So if it tells you to put in like one battery, that might not even make sense. Like sometimes these integrated battery systems, they only come in certain sizes. So I went ahead and put a limiter in there to not allow you to put in a system that's lower than 180 kilowatt hours, because it's the smallest integrated system that we're aware of right now. But you're welcome to design any size system, but just keep in mind, I want to check and make sure this is feasible or just kind of makes real world sense. The tool does not represent every system type, so check the calculations to make sure the system type you are considering actually matches. Feel free to go into the actual cells and say, I'm thinking I want to put in solar with a grid-connected inverter to the utility. Does this calculation actually match what I'm thinking of? Don't just blindly use the spreadsheet. And yeah, feel free to add columns. Sometimes it makes sense to even put in batteries without solar, and that we don't have that by default in the spreadsheet, but there are some cases where that might make sense, where the utility is really inexpensive. Well, I hope you learned something and enjoyed the presentation.